Hello, welcome to noise control and its management. Today is the third day of this particular week of the course, and what we plan to introduce today is again a continuation of the side branch mufflers, but in this case we will be looking at mufflers which are essentially closed tubes. So, here is the side branch muffler, it would look like. So, we will discuss side branch mufflers. With closed tube. On the side. So, how does a muffler look like? So, you have, let us say you have sound going through this tube. So, you have power in and power out, and you want to reduce the value of W out. So, what you do is that so you have this tube and then you put a tube here, just a long tube, and the diameter of this tube could be 2A. This tube is closed at its end, and you may or may not have an acoustic resistor by putting some wire mesh here. Okay. So, this is a side branch which is a closed tube, and this also acts as a muffler. So, again this tube has its natural resonances, and at each natural resonance it will suck in sound, and through the process of reaction it will eliminate the sound which will be a part of W out. Now, understand that we should understand a very important property of closed tubes. So, suppose I have a closed tube, a tube which is closed at one end and it is open at this end. Closed tube can generate several natural modes. So, it could, so suppose I want to plot velocity inside this closed tube, velocity at the closed end will be 0. So, it could become maximum here. So, it is like this. So, this is what? This will be 1/4 of lambda. So, this dotted line is the spatial envelope for velocity in a closed tube, and this is something we have discussed earlier in our earlier classes. So, this is mode 1 or the first resonance which can exist in a closed tube, but in the same tube other resonances can also occur. So, again the tube is of the same length, and so I will draw this line actually continuous, something like this, but here another mode which can develop in this closed tube could be something like this. Something like this. Now, this is, yeah. So, this is 1 lambda, and the entire length here in the entire length of the, so between 2, this is 1 lambda, and this entire length is 5 lambda over 4. Okay. No, excuse me, I am sorry. Okay, so I made the third mode. I will redraw this. I will make the second mode and then I will make the third mode. So, I am sorry. So, this is my closed tube. So, this is the central line. So, it could look like this. This is the second mode which can develop in a tube, mode 2, and here the length of the tube equals 3 lambda over 4. Okay. And then I can have a third possibility and a fourth possibility and a fifth possibility and so on and so forth. So, here this is another mode which can develop in a tube. So, this is mode 3 or the third resonance. Here the length is still the same, but the wavelength which can resonate in this tube could also be 5 lambda over 4. Okay. So, lambda over 4 equals L. Here 3 lambda over 4 equals L, here 5 lambda over 4 equals L, and so on and so forth. So, the point is that all these resonances can exist, can develop in a closed tube. So, if I attach such a tube to the side, it will have a natural tendency to suck in all the sounds associated with lambda, this frequency or this frequency or this frequency and so on and so forth. So, that is where. So, the resonance, so what do we say? We say that at resonance, the wavelength of the sound could be 2 LC divided by n minus half, where n is equal to 1, 2 and so on and so forth. Okay. So, if n is equal to 1, then the resonance, the wavelength at resonance is 4 LC divided by, what is it? Yeah, 4 times the length, and the associated resonance frequency is what? C over lambda r, and that equals n minus half times C divided by 2 LC. So, if I have a particular tube length, associated with tube lengths, I will have a large number of frequencies, infinite number of frequencies which can resonate in the tube, but they will be discretely separated. It is not all, they will be discretely separated. So, for all those frequencies, this tube will act as a good side branch muffler. So, next what we want to look at is what is the attenuation coefficient for this kind of a side branch muffler. So, again I will directly write the results. So, attenuation coefficient for such a is 1 over 80, and 80 is the transmission coefficient, and that equals, and I will explain these terms, sigma L, where L is the length of the tube, plus Rs over rho naught C. We have already described what is Rs in the last class, plus pi a square by 2s, where S is the cross sectional area of the main pipe. So, this is the cross sectional area of the main pipe. So, this entire thing squared times tangent of KLC, where LC is the effective length of the tube. L is the actual length, but LC is the effective length, and we have discussed how to calculate effective length earlier, plus 1 divided by sigma L plus Rs over rho naught C square tangent of KLC plus 1. Now, here what is sigma? Sigma is the attenuation coefficient of tube. Okay. So, what does that mean? Basically, when air is passing through the tube, this long tube, this is a tube, not a short tube, it is a long tube, and because the air is inside it, it has a tendency, some the sound will get dissipated, some of the sound will get dissipated and get converted into heat. So, that is what is meant by attenuation coefficient of the tube, and this is equal to pi times mu c f divided by rho naught, the entire thing under the square root sign divided by AC. So, A is the radius of the tube, rho naught is density of air, f is the frequency of interest, mu c is effective viscosity. So, if air is not viscous at all, then the value of rho will be 0, because no dampening will happen because of this thing. But mu c is effective viscosity, it is not actual viscosity, and what is mu c? Mu c is equal to the actual viscosity of air times 1 plus gamma minus 1 divided by gamma PR whole thing under square root. And what is gamma? Gamma is what? Cp over Cv, it is a property of the gas. So, typically for air this is approximately equal to 1.4. So, unless it is a very special gas, a lot of times we take gamma as 1.4, and PR is what? Prandtl number of gas, Prandtl's number. So, again this will be given, Prandtl's number of, or you can get it from charts and things like that, Prandtl's number of gas. So, if you know the gas, you know what is gamma, what is Prandtl number, and you also know what is the viscosity of the gas. So, with this you can calculate effective viscosity. Once you know effective viscosity, you can calculate attenuation coefficient of the tube, and that you can plug into this relation and you will get how much sound is lost as it passes through this thing. And again transmission loss is what? 10 log 10 of 1 over AT. So, for this side branch muffler, this is the transmission loss. So, we can calculate transmission loss in such a way, and couple of things. So, see what happens. So, we will look at this relation. When k times LC equals 0 or pi or 2 pi or 3 pi or n pi, then what is the value of this tangent? It becomes 0. So, for particular lengths of this tube, k is what? Wave number, right? K is equal to 2 pi over lambda, that is the wave number. So, for particular lengths of this tube, tangent of k times LC will be 0. So, this entire thing in the numerator will be 0 except 1, and also in the denominator you will have only 1. So, this thing will be equal to 1 when tan KLC equals 0. Okay. When tan KLC equals 0, then this will be 1. And what does that mean? That 1 over AT equals 1, which means the ratio of W in over W out is 1, which means no sound is getting absorbed. So, for certain lengths of this tube at particular frequency, this side branch muffler will not absorb any sound, but for some other frequencies it will do a very good job in terms of absorbing sounds. So, when will this number be maximum? 1 over AT will be maximum when tangent of KLC is close to 90 degrees. Okay. So, then what will happen? This term will be very large and this term will be very large. So, the contribution of one can be neglected, and in that case I can omit plus 1 on the numerator and I can omit plus 1 in the denominator, and then especially when tan KLC is 90 degrees or actually this should be tangent square, I am sorry. Okay. And in that case, if I can omit plus 1 from numerator and denominator, these tangent terms will cancel out. So, 1 over 80 will be maximum when they are when it will be maximum when tangent of KLC equals infinity, that is when KLC equals 2n plus 1 times pi by 2, okay, 2n plus 1 times pi by 2, and in that case what will be the value of 1 over 80? In that case 1 over 80 max will be equal to, so 1 goes away from numerator and denominator because its contribution is small, tangent square gets cancelled out. So, what we are left with is, so it is equal to 1 plus pi a square by 2s divided by sigma L plus Rs by rho naught C whole square, and the entire thing is squared. Okay. So, basically this result in the numerator gets simplified to this simple thing. Why? Because tangent square gets cancelled out, and if I divide this thing sigma L plus Rs by rho C with this, I get 1, right. If I divide the sum of these two by the denominator, I get 1, and then I am only left with pi a square divided by 2s divided by numerator. So, that is what I get here. Okay. So, this is the maximum possible sound reduction coefficient, and in that case TL max is equal to 10 log of 10 over 1 over 80 max. So, what we will do is we will do in, no, there should be a square, yeah, because there is a square here. So, that in the denominator you will have the square term. Oh, I see what you are saying. I have squared it twice. So, that is, yes, you are right. So, what we will do is we will do an example. So, what we have is a side branch muffler and in this case it is a closed tube. So, side branch is not a Helmholtz resonator, but a closed tube, and the diameter of this pipe is D, sound is going in, and it is the wattage going in is W in, wattage coming out is W out. Okay. This diameter of the side branch is 2a, the length is L. Length is L. So, here is what is given, 2a equals 54.8 millimeters. The diameter of this main tube is 161.5 millimeters. Temperature in the tube is 21 degrees centigrade. Pressure is 101.3 kilopascals. So, for these conditions the density of air is 1.2 kilograms per cubic meters, velocity of sound is 343.8 meters per second, We are also told that the Prandtl number for the gas which is flowing in is 0.710, oops, so it is 0.71, gamma is 1.4, which is the ratio of Cp and Cv, and the viscosity of air is 18.17 times 10 to the power of minus 6 pascals second. So, all these data are given, okay. And we want that tube should work at 250 hertz. We want the tube should work at 250 hertz, okay, and it should be shortest tube. We do not want a very long tube, because we can have several values of length. It should be shortest possible tube. So, for these conditions we have to figure out what is the TL, transmission loss, and then we also want that TL, once we have designed the tube, that is once we have figured out the length of the tube, for that length of the tube what is the transmission loss at 177 hertz. 177 hertz. And the last thing which is given is that in this tube there is no mesh in the tube, there is no mesh inside the tube, okay, because I mean we can have a mesh, but in this case we do not have a mesh, oops. So, that is there. So, we have set up the problem and we have barely a minute or so left today. So, what we will do is we will close for today, and tomorrow we will again revisit this problem and we will quickly solve this problem and move on, but this is the overall problem formulation. And what we plan to do is we want to calculate the transmission loss at 250 hertz and 177 hertz, and it should be having its maximum transmission loss at 250 hertz. So, that will help us define the length of the tube. With that we close for today, and I look forward to seeing you tomorrow once again. Thank you.